Hello guys. I was just raising the board, the people in the room, we're seeing that video later. The computer club was just had a meeting and was planning some upcoming events. So some really fun events coming up for the computer club. A lot of them are gonna be sort of a mixed thing, kind of like our classroom is here. We have that learn anywhere equipment now. So we have the big monitors here in some of the rooms, good Wi-Fi connections. So things like our game jams, movie nights will be both Zoom call and in person. Starting to get back to social situations is nice. But the club is working on planning that, putting all that together. So that's some social things coming up soon. That'll hopefully be fun and enjoyable. There was talk about conferences to some different conferences the club could attend, or maybe do view parties for, and a bunch of interesting things there. So that might be something in the future to keep in mind for the future, because it's good to socialize, right? Be around people, talk. We're social species. Even if most IT people are introverts, it's still nice to be around people sometimes. So this evening, we're gonna kind of pick up where we left off the other day, looking at data structures. Which is an important concept. We want to get our data. Well, a couple weeks ago, we looked at long-term storage solutions, a bunch of options there. We want to get the data from long-term storage into our processor, RAM, through the CPU, do all of that stuff, and back out of RAM as smoothly as possible. There's some traditional data structures to go over, and go. It's fairly standard in classrooms to look at the most basic versions, which sometimes seems a little strange because a lot of our languages have them work in there. But I want to take it a step further, kind of like we did the other day with lists, and include those simple concepts like make a list in our objects themselves. That way we don't have to use that default list. We can use a very one customized exactly to our purposes. And the big thing is just to kind of go over the concepts, understand what's going on with them. The next one is a word that I know you all have heard. You remember back at the last Thursday, we started looking at data structures with linked list. So the next one is a very common one. And actually, I'll write the next two. Stacks and queues, because they go together. They're very, very similar. Just a slight order change between them. So I'll put a stack over on this side and a queue over here somewhere. That's probably enough room to make the list. So a stack is last in, first out. Whoops. Let me try that again. A stack is going to be the last in, first out sort of data structure. Or LIFO, since the acronym for that does spell out a word. We don't have to modify it into an anagram or anything. And a queue is sort of the other direction. That's going to be a first in, first out data structure, or FIFO. The idea is similar. The items are loaded in and removed as needed. Dynamic list, we don't keep things around. We put stuff in our stack and get them out of the stack as quickly as possible. The queue is kind of the same thing. sort of a contrast to, like, say, a dictionary. Right? When we put a dictionary together in a piece of software that sticks around, we have to have it there the whole time. So we have those key value pairs, so we can't break it apart and have the computer reassemble. Once we put it there, it's there for as long as the software is running. Stacks and queues are much more commonly used to get stuff processed and out of RAM and the rest of the CPU as quickly as possible. What I have in my notes, dictionary in which everything must be kept in RAM the entire time, whether it's currently needed or not. We have a great big long dictionary and we just open our software briefly and need one item out of that dictionary. We have to keep that whole dictionary in RAM the whole time. And we kind of saw with recursion when we put together that key diagram talking about what was going on. That's the most natural data structure for a machine. Whenever we just kind of flow with what's natural for the machine, like in recursion, where output becomes input, and that's how we get our repetitive structures. The machine essentially builds a stack itself, builds up the stack and then pops things off the stack. So when we have customized stacks, there are some efficiency advantages over other types of customization. Just like linked lists, this is a traditional point in programming classes. In the most generic sense, kind of see what it's about, get the terminology for a stack. And we'll look at an actual example of that. So some key terms, the vocabulary part, right? That's a big reason we look at it in classes. I'll label it that way, vocabulary. There are a number of words, the big three, or actually I'll put 4 on here. Our words for a stack are going to be push and pop and peak. Are the main terminology to go with it. Or not, maybe I'll just put the 3. The 4th one I was going to put there would be size, where we ask how many elements there are. Might as well do that because that's going to be in our example. How many things in stack? Peak, that's where we look ahead at the next item in the stack. Or I should probably write the word element because that's a proper term for it. The next element in the stack. Pop removes it from RAM for processing. So internally in the CPU, what it does, that in the pop instruction takes it out of RAM, leaving and sort of leaves in the indication behind that it's not coming back to RAM, so that spot can be used for something else. So it takes it out of RAM and pushes it over to the registers so it can go through the ALU and actually be processed, whatever it is. So pop removes next element for processing. So it does actually return stuff. We're going to see this in an example here in a moment. Hopefully the terms will make a lot more sense there. Push adds another item to the top of the stack. Adds an element to the top of the stack. I'll come back and talk about queues in a moment. I ran out of room to write there anyway. I'll put that over here. Got plenty of room on the board. I don't know why I put them so close together. So those are our big terms that we want to think about when we put together a stack. Pushing things on the stack, popping things off the stack, peeking at what's coming in the stack, and the size, which unlike lists or dictionaries or tuples, the ones built into the language, that's going to change constantly because we dynamically add things to it and take things away. So the size is constantly changing. So for one, for loops can be problematic. We usually don't use a for loop on a stack because the size is going to change on us. Things can get added to it. And the standard example of a stack is the dishes after being washed. Trying to avoid that word in the example. After dinner, we wash our dishes, start putting plates away, and the plates just sit one on top of each other. And then when the next meal time comes around, the last plate to get washed is at the very top of that pile, so that's going to be the first one to use. Or laundry day. And after when we take a shower, clothes get thrown into the hamper, and then when we're ready to do the laundry, we grab from the top of the hamper. So the last dirty clothes put in the hamper, the first thing to go in the washing machine. That sort of structure. The last one in is the first one out. And it is kind of prepared in Python. There's some of those words you might recognize are already available with our list. And actually, when our textbook did its generic example of a stack, that's all it did for the pop method. It just used the built-in pop method, which pulls off the end of the list. So if the change ours up a little bit, I was going to use the front of the list that way we're not using that way our pop method doesn't just call the pop method that's built into the language. We're actually seeing something different. Let's see, I better open Spider here. Yeah, the computer club thing was running a little bit over it. It just ended about the time the first person came into the class. So, but that is an exciting thing. It's after the whole lockdown and switch to virtual, and the new thing seems to be a mix, right? Like the classroom is here. I'm here on campus in the classroom, so if you don't want to join me, you could. Or you can just log on from the Zoom call. Both options are available, and all the club events that they were planning this evening seem to be following suit with that. I think I still have the files from the other day. I tried to leave them in the delete folders and go right back to where we were on Thursday. Okay, good, I didn't delete. So started the other day building up some classes and just we saw that's all it takes to build a list in the most generic sense. It's not a complicated thing to build. Is part of the reason that's available in every language, because when we went a little further and started customizing it, it was quickly evident that it's really just that one line is what turns a custom class into a list of things. When we did that as an example, we gave them all names, but we wouldn't necessarily have to do that. Yes, our custom one here, we have the boss, we make that the first one. And then we gave reference names, but we could have just done that as one long line. So boss is the ds.crew. I'll just copy from this with all of this stuff. Or I'll put it to the word team. So then that boss, it has a next element. That's gonna look messy because we haven't looked at anything like that. Next is the next ds.crew. And get the second one in there. And then we can keep building it up from that. Next, that next thing, well, it has a next data field as well, which again is going to be this ds.crew thing. Or team.next is the last one. So I'm getting ready to delete that, but do those lines of code make sense? And probably show a clear need for an append method, like what we have in the Python list. Becomes very evident when we keep adding that, just reusing that same variable, the .next. But hopefully that makes sense. We could have done that, and then it would look more like a list in the sort of thing we're used to. And we can also see the iteration there. Because each iteration just goes to the next element. That's all the iterable part would be. I'm gonna clean that out of there because that's a little bit of a mess, but I wanted to at least show it that way. So we saw it doesn't take much to create that. Stacks have a little bit more to them, a few more lines. It's more than one line to create it. We could actually use this list we created, but I'm going to go ahead and use the built-in Python list to make our stack instead of our custom one there. Well, first off, I'm going to add some white space because y'all are aware I don't like typing at the bottom of a screen. So we need a new custom class. Call it a stack and start putting it together. So the first thing is, if I draw a picture, we've seen those stack heap diagrams before, right? The standard picture to represent our code. So we start stacking things up, but then we pop them off there. So we'll push a few instructions on the stack, pop some of them off, push a few more instructions on there, pop a couple off, and our stack is constantly getting bigger and smaller as the code runs. So when we get to the end of our software, it should look like that. So at the beginning and end, we should always have an empty stack. So one thing is our constructor shouldn't need any elements passed in because we always want to start with an empty stack. We want to start and end with an empty stack. That's kind of how we tell we're done when the stack is empty again. So just to give it a name, I'm going to call it stuff. And I'm also going to use the double underscore to prevent it from being easily accessible from the outside. I think y'all are aware we can get right to it. All we have to do is type underscore stack, underscore stuff, and we have access to it. But it's the closest thing we have to private data fields in Python. So we can do that. So we have this nice little enclosed list that we're going to use to build a stack. And then we'll set up our methods. So we'll want our keywords here. We'll need a way to add stuff to the stack. So that'll be we'll need a push method, self, and then the item we want to add, which I'm just going to do the headers for now, and we'll come back and fill in the code. So that puts stuff on our stack. One way to get things off of the stack, or the big one, the pop method. Which we'll come back and get the code, and I'm just setting up the method headers first. Oh, the third one on there, peak. We want to know if there what the next thing in the list is, because we might need that as a pause point. Right? When I was drawing those lines, it kept getting bigger. Our stack was growing and shrinking. But sometimes we might need to look at that to see if we're ready to pause and add more stuff or clear it out. Maybe our stack's being used as a buffer. Right? We can't load in the full movie, so we load in a part of it and then feed that through. And whenever it gets low, we want to load in the next part and kind of keep it going. That would probably be a queue, which I erased from the board. But we'll get to that here in just a moment. We might want a size thing, tell us how big the stack is for the same reasons. Peek ahead to see what the next one is, or just check the size of it. And for our purposes here, at least for certain, we want that toString method so that we can see what's in our stack at various points along the way and do some comparisons. So return cast as a string self dot underscore stuff, which for our purposes here in the classroom, we want to see the whole stack, because as we do different things, we want to see that dynamic part. So we'll just look at the whole thing. And now for our methods. And I'm going to use the beginning of the list to break away from, well, like the book did. Python, the lists do have a pop method. So we can kind of treat it as a stack, and that removes the very last item from our list. I'm just going to shove things in from the front, if that makes sense. So like here would be index 0, and down here is our length -1 index. So that we'll put stuff in at 0, and then we'll take stuff out from the front instead of the back. That way it's different than the built-in list. That way our pop method doesn't just ask for the Python pop method like the books did. So we'll put stuff into index 0, which is fairly straightforward because we just use that the Python list. It would be straightforward even if we would have used our own custom list here as well. Stuff, we'll ask for that list. And we want to go to the beginning instead of the end, so we need to insert that. At index 0, insert whatever that item that was passed in was. That's all we need to do for that. To pop it back out of there is a little bit more though, because we want to actually remove it from memory. We need to fully remove it. So I'm going to do this in a couple lines. We'll just take note of what it is. Actually, we'll grab it. We'll make a shallow copy of it so we still have it. And then we'll delete it from our list or remove it. Stuff.remove the top. If y'all haven't used the remove method before, the remove method does need the element we're looking at. So it's not an index. If it's a number, like if we have a bunch of numbers in there and the very top one in our stack is 3, we put a 3 in there and we'll say remove 3, and it'll know to remove the data 3 from the list, the first instance of data that's in our list, and not the very last one. Which remove is actually the keyword from queues. One of our keywords, we'll see that in a moment. And then we'll return that. So you can see, instead of just grabbing it and using it, we actually removed it from our list. So we could just as well call that line right there. I don't think we've seen that, have we? We'll look at that tonight. So we could manually go ahead and tell the garbage collection to go ahead and use that generation equals 1. I have to import the library. We'll see that tonight. But we could take it out of our stack and immediately tell the garbage collection to grab. It's like, don't wait 30 milliseconds for the next pass. Take it out of memory now. We don't want to waste 30 milliseconds that could be used elsewhere. I don't think we've seen the direct control of garbage collection yet, so we'll look at that later. So we're actually taking it out of memory. It doesn't, unlike our normal list, we don't just use it and then do other stuff while it still hangs out. It's actually been removed from there, so that the stack will fill up as we push things on and then empty back out. And much more efficient usage of memory. Also gives us a good place to check and see when it's done. Peak is almost the same, except that's what we normally do with the list. So I've got the stuff list again, index 0, and instead of actually taking that out of there, we're just going to look at what it is. So we'll return it, but it's still there, right? That's the one we're used to seeing. We just kind of grab what it is, but we don't change it or anything. And size is just as easy. Return length of self.stuff. So it should look fairly straightforward. The trivial cases, you can see it doesn't take much to put that stuff together. And actually, if we would have used this up here, well, you saw it didn't take much to do that. So we could have done our own custom list here, but I'm just hoping y'all can kind of fill in that gap, right? What's a good name for it? Base. So the start of our stack is another LL. What do I call it? LL node. And then we just set all our stuff up that way whenever we push stuff up. Actually, might be better to do this. Start with it none, and then when we pass stuff in, self.base.next is what we're doing. Self.item is a LL node with the item we just passed in, with the next one pointing to self.underscore. We want to go that way with a list. So we pile it on top of our previous one. And then when we get all the way back to that one that is none, that's our empty stack. And then popping it would just be removing it. We'd probably want to actually call the delete method. I'm going to comment those out so we can see sort of an alternative. I guess that's a useful thing for a comments. We can put alternative ways to write our code and then just swap out what's commented. So we could return whatever the top item is. I think we still need a counter in there, but hopefully you can at least see the idea that we can use a custom list to do that. Really what we're gonna do, we'll see in a moment. We just want to mostly get the key vocabulary terms. Our list already have those. So we wouldn't ever make a generic stack in Python like this. What we would make is a customized stack. But first off, let's kind of look at what these things do as if it would come as a surprise. So I'll import that. PT sounds like a good name. What did I do in my example? Did I do anything fancy? I think it was this one. We'll call that DS. That just makes more sense than DP. I'll print a couple line breaks, make sure things are spaced out so we can see it. Print, we're going to bring in a stack. And, oh, PS.stack. Nothing too fancy there. So that gives us our empty stack. This point in the picture, we have a place to put things, but nothing in it yet. So we can push a few things on. I'll just do some integers for our generic example. Push into 5s, stack.push 12s, stack.push 31. And I'll print. So just calling that pusher method a couple of times to put things on here. Did I spell it wrong? P-A. Oh, there it is. Let's try it without the typo. Oh. So I did not notice that at all, but somehow the word stuff got typed twice. There we go. So we have a couple things in there. Our stack, and it's in such an order that the last one in is now our first element. So that's why I went with 0 instead of the way Python does it, where the last element is the last index. Our last element that we put in there is our first index. To change it up a little bit, and yeah, really mostly that was just to avoid doing this by only calling that the built-in pop method, which goes from the end of the list, not the beginning. Maybe I'll print that out twice. And then the new stack. So you can see we get those elements because we do actually return them when we pop it off the stack. So popping is grabbing the thing off the stack, right? There you got a stack of papers here. So when I pop the first thing off there, it's not part of the stack anymore. It has to actually be put back into the stack if we want to use that again. So then we could put a couple things on there. Stack push 3 and push 8. I'll be consistent. I started thinking maybe I should put some new lines in there instead of typing print a bunch of times, but might as well be consistent here. That's probably enough for our generic example. I think y'all get the gist of it. So we start with an empty stack, build stuff up, take it out. I should probably print the empty one to begin with. There we go. So it starts completely empty. And then as our software progresses, we add things to it, take it away. So it does make a difference in memory. But I was looking around and couldn't really find a good way to measure it. To introduce in our class. Where'd they move task manager to? I know at least one place it is. Tried using this. This would be like the bare minimum. We can see spikes on the CPU go up and down, but really we need to create a very large list to see it go into memory and come back out. So maybe I'll do that for I in range of 1,000. That might work. I'll add it to the list. Just a blank thing. So I can't remember if I had NumPy on here or not. Apparently I do. Oh. This is what we can at least see those little monitors a little bit. So when we fill up that list to do stuff with, oh, what's not callable? Oh, not print. Is that what it is? There we go. Yeah, I can't really see much of a difference. Any difference in the numbers here? Let me close that out of there. Make the list really big. And hopefully we can see the little picture. Nope, it didn't seem to have any effect at all. Yeah, I was looking around and couldn't really find a good way to measure these with the tools that are available. Yeah, because the one here isn't really giving any information. I'll look into ways to measure this. We're gonna have to do this on Thursday. This what I thought I was gonna do originally didn't work. And well, when I tried it on my office computer, the task manager was at least able to show the stuff. You can see a little blip in the memory graph on the task manager, but that doesn't seem to be working on my Windows machine. If I was on the Chromebook, you might see a little bit more. But I'll look around for ways to measure this stuff so we can compare the difference. Hopefully the idea there makes sense, because ultimately we want to get back until we loop until our list is empty. So our loop usually looks like this. While stack.size is bigger than 0, we just keep doing stuff. Push numpy.random.rand, and then print stack.pop. That loop right there is essentially what all pieces of software do. It just happens in the background. The programming language is already set up to do it because it's not a difficult thing to set up, right? Just a couple lines of code. Just see how much is left in our stack, because that's how, well, this Python code right here. We write the text file, the computer reads that backwards. So in our case, it's going to read from line 67 up to 1 to make a stack. So then line 67 is here at the bottom of the stack. Line 1 is up here at the top, and then it starts popping those instructions off, sending them to the Python interpreter in a loop like this. I mean, yeah, that's going to throw an error. Oh, no error. It looked like it all worked out evenly. So we added some stuff, added one thing, and then popped 2 things off the stack and kept that going. Or to see it more dynamically, push 2 things on, and then pop 3 things off. And then print the stack. So a very dynamic structure. It gets bigger and smaller as it goes. It grows and shrinks and grows and shrinks. So we had 3 elements. Added those 2 things, pulled 3 off, then we're left with 2. Added 2 more things, then we had a bigger list. I should have printed it there. Pop them off immediately, along with the previous one. Add that, added the next 2, popped them off immediately, then popped off our original one, and then our little piece of software is done. That's the main reason to look at stacks. We have them already built in our language. They're available everywhere. But that is what the computer actually does. So in the background, you can see it's not very hard, so that's already been written. But one of the things in the background that might have always seemed so mysterious and so fancy is just that right there. So you can see that background stuff, putting the language together isn't necessarily a big complicated process. The computer can handle a lot of that. Queues are going to be very similar. And then we'll finish up with a useful example instead of the stripped down one that is even less than what the language itself has built in. We just want to kind of look at the key concepts, and then we'll look at a customized one, is my rough plan for the next half hour, I guess. So going back over to data structures, the queue is going to be very, very similar. We have some different terminology though. So I'll write the vocab words on the board again. That seems like a good place for them. This way. That'll work. So quickly about a queue, it's much like a stack. The elements are loaded in and removed as needed, not kept around in memory, wasting spots in RAM, which the biggest thing about that, as opposed to, well, we saw last week, I think, maybe the week before, whenever we looked at recursion, there was a time when recursion was way faster than anything else, because that's what the machine naturally tends to do. Some of our programming languages don't even have loops, and not just the ones that have been around since before loops were invented in the 60s. I guess the idea might have been around some of the 50s, but people just custom made them when they needed them. Some of the languages have been around that long, but other languages that have been developed since then, people didn't bother to put loops in because recursion is natural for the machine. It was much, much faster before the days of parallel processors and multi-threading, because recursion is also very resource intensive. If we just have one thing going, so recursion is excellent for microcontrollers, where the whole purpose of it is a little reprogrammable chip that runs one script over and over and over forever. Recursion's great there because there's only the one thing happening. So we can get more speed that way by doing what the machine wants to do. But nowadays, we saw it when we tried to time our recursion example. So with other things going, like the Zoom call and whatever else my laptop has going on in the background, all of that stuff runs concurrently. Some of it's synchronously multi-threaded, some of it's asynchronously multi-threaded. Parallel processors are common. We have lots of different things happening, not just one single thing. So recursion is kind of ineffective. And that's where stacks and queues come in especially important, because other things could use that memory. Y'all have probably seen it now by this point. Education's been very much a Zoom thing for about 2 years now. So you've probably seen many Zoom calls get slow because start to run low on memory. Or while on a Zoom call, the browser gets really slow and things start to slow down. So that's why we want to use stacks and queues, because we're not wasting our RAM. We use what we need, get our stuff back out of RAM, and then something else that's running concurrently with our software can use that spot in RAM so that the overall process of the machine doesn't slow down. So the next one to look at is going to be queues. Much like a stack. Oh, this one. That funny word in English, 5 letters long, but 4 of them seem to be silent letters. It's first in, first out. So just like we did with the stack, I'm going to try to align that to the indices. So we'll put things in, the first one in gets our lowest number of index. The first one in gets 0, then 1, then 2, and we'll add them in order. So we're adding them to the back of the list. The standard example to this is a queue is like a drive-through. I'm not in the video there. Okay, so a queue is like a drive-through at a fast food place. The first person to get there is going to be the first person to place the order, then pull around and get first person to get their food. And the people that get there after them get behind them in line, then they go next, and it just goes in that order. The first one to get there is the first one to get served. Same thing with our data. The big difference with cues is there are typically two sets of vocab to go with them. So to put stuff in a cue, we have either the words on cue or poll. And to take out is this word. I don't know the background for it. It looks to me like somebody just put D, the opposite of in, like D, the prefix for undo, so like DQ, but we pronounce that deck. I have no idea who came up with that either. So on cue and deck, but that's how we spelled. That's apparently how we spell deck. Somebody spells deck. Although I'm sure if you said DQ, most people would know what you're talking about. And to take out, the one that usually goes with poll is remove. And these are sets of vocabulary, kind of like when we have the class inheritance relationships. Like we say parent and child, and it means the same thing as superclass and subclass, but we would never say parent and subclass because those pairs don't go together. Or you wouldn't say superclass and child class. The things come in pairs. So it's like these two go together, these two go together. Personally, I like poll and remove. I'm not really sure why. I don't know if I really have a good reason for them. And then both sets have those other two that we saw with the stack, a peak and a size, which do the same thing. Look ahead at the next element of the list without actually taking it out of the queue. So it's still there in line waiting to be processed. We're just checking to see what it is. I guess a good example of that, the place to use the peak one didn't really show up. Let me actually use that peak somewhere in our stack. Oh, whoops. To kind of see the difference between peeking ahead and just checking the size. Because I think the only place with the simple example we did here, the only place that it would really kind of show up is when we were in the loop, kind of equivalent to checking for the size, to peek ahead and see if we're done. But it would be used more often to see what the next one, if it's the next one's the element we want. So I'll take out these print statements and just fill the list up to what it was earlier. And then kind of loop through it. So while stack.size is bigger than 0, so our loop would pretty much always look like that. What we're going to do is maybe see if we have an even number. If stack.peak at the next thing mod 2 is equal to 0, then we want to print that number. Print stack.pop. If the next thing's even, we'll print it. Otherwise, we'll just pop it off the stack to get it out of our way. Oops. Stack.pop. So that's where we would use peak. We look ahead and see if it's the one we want. And, I can use my notebook for an example here. Right, we're looking for a particular thing. I guess I didn't need blank paper. I could have used the other one. So there's a trash can right here beside me. Oh, that's not the camera. This way a little bit. There's a trash can right here beside me. And I have a stack of paper. So I'm gonna check the top one. Is that what I want? No. Throw it away. Is that what I want? No. Throw it away. Is that what I want? Oh, that's the one I want. Throw the rest of it away. So that's where a stack is, right? I no longer have a stack of paper. I only have that one that I wanted. And that's where we would use the peak method at as well. I guess I could save that. That's all blank paper. I have a whole bunch of sets of notes that probably would have worked great for that example. I didn't think about using them until I ripped a bunch of blank pages out of the notebook. So that's what this loop is doing. Go through our stack, see if it's the one we want. If not, throw it away. Quit wasting memory with it. Oh, whoops. That's not throw it away, because the only thing we have to do is put it on the screen. That's what I meant to do, sorry. So we only print out our even numbers. Where'd that 31 come from? Oh. Something unexpected happened there. So we have an empty stack here. Oh, that's those lines. Let me try that again. There we go. That's how it works. So we wanted the even numbers. So we just threw away everything that's not an even number. And even when we grabbed them, we took them out of RAM, so they're not sitting around wasting any space in RAM. Oh, 7 o'clock. I guess we're not going to get to the garbage collection. But we're going to talk about data structures for a few days, so we'll see those. So Q is kind of the same thing. We peek ahead, and then our size, we always use that to see if we're still, if there's more things to do. Is that everything that's in there? The notes here are very, very similar. Repeat of we're going to look at a generic one here first. The specific example would probably be exactly the same for the example we're going to do. It won't really matter if we do a stack or a queue. The only difference is whether we pull from the front of the list or the back of the list. Might be a way to think of it. Yeah, so we'll do a little example, but first off, just the generic queue and what it looks like, which is going to look very similar to the stack structure. Class queue. Because again, it needs to start as a blank list. And that's all we want when we start, right? When we open a deli in the morning, there's no customers there. It's an empty queue, to actually use that word in the traditional British English sense, right? Where a queue is a line that we stand in. So we start our business day with an empty queue, and we end our business day with an empty queue. So same thing for software. We start with an empty queue, and then we're done when the queue is empty again. It's kind of how we know what's going on. So we'll just set up again this semi-inaccessible stuff list, which we could use our own list, but our own list, custom list that we made the other day, might need some sort of index counter to keep track of things. For when we add more things onto it, using the pre-built list is a little easier. We just need to see the basic concepts. When we get to a custom item, it'll make custom item. When we do our own custom classes, we're not going to use the built-in, or we are going to use the built-in list. Sorry, I did not mean to put not in that sentence. So I'm going to use this set of words, poll and remove, but on queue and deck would mean the same thing. I guess it comes down to a matter of preference. So I'll define a poll method, take itself, an item, and for now, I'll just set up the method headers. Then a remove one, the self, pass, define peak. And size. I'll go ahead and finish that one out. That one's not really part of our queue. That's just so we can see it in our generic example. So you should notice right off the bat that both, one thing they definitely both have in common is the only method that takes in any parameters other than that default one that has to be there, the self-referencing parameter. The only one that really takes in any parameters is to add the one to add things to it. All the other methods are the parameters we would need to carry out that task are built into the definition of what it is to be a queue. So I'm going to stick with that, go the same order. So the first out part is going to refer to our 0th index. And so we'll add stuff to the end of the line this time, which is our last index. So stuff. It's just our normal append method and just throw that item on there. That's all we need to do for that. But when we take it out, it'll be sort of similar. Here we could just use the pop method because that would pull from the end list, but I'm going to spell it out the same way as we did earlier. So we'll make a shallow copy of it so that we can actually remove that spot from our list. And then we'll return that. So, got an equal sign. So once again, we're actually taking it out of RAM. So since we use the default list to keep this example like cleared of clutter instead of our list, it doesn't fully leave RAM because that list has preset sizes, right? As soon as we say we have a list, we have room to hold 8 objects. And as soon as we get that up to 6 objects, we have room to hold 16 objects. So it's that dynamic stuff built into the internal lists. There's still an empty spot there. So our example is a little bit oversimplified where we don't really see that, but hopefully the idea makes sense and you can see the usefulness of it. For when we look at the actual custom stuff here in just a moment. Peek ahead, it's just like on a stack, we're just going to look at the next one. Stuff. And the next one is, we want to grab the first index. The first out is going to refer to our, we'll take out from the first index. The oldest thing to be in the queue, the thing that's been standing in line the longest. Size will be exactly the same as well. Return the length of that stuff list. A new file, I'll call it QTest. And the QTest is, well, it's very similar to our stack test. I want to run these side by side. Actually, I'm going to put them together. I'm going to do the same thing everywhere. Now I'll just do this. Copy. Run that. So there's our stack list. And I think this will work. I'll paste this here and control R to replace the word stack with the word queue. Oh, zoom buttons are trying to be difficult. That one means capitalized, I think. I have to change those other words. So push. Control R, replace that with poll. Or on Q index. I should add a comment in there. Poll or on Q and remove or pick. I think that's the reason I don't like using those terms. Because I know how that's supposed to be pronounced and it just doesn't seem right at all. And then we'll replace pop with remove. And zoom buttons are being difficult, so I have to wait for those to go away. Here we go.
Ralph Lauren.
Where'd that crash at? Line 88. Oh, was that over here? Oh, I might have been misspelling that. Somebody put in the chat room that I put an extra UE when I wrote it. I actually spelled the whole word out DQ. Where's this error happening at? Return this. You should have. Oh. Okay, apparently I put 3 underscores instead of 2 there. Sorry. There we go. So we can see the differences side by side. So if I roll up to the console, run the stack. There we go. That way there's nothing else in there. Oh, I'll do the same thing here. Eventually, I'll hopefully get up to the example I wanted to point at. Okay, so you see the order of the stack is reversed from the order of the queue. Same thing when we take them out. We took out 31 and 12, still have the 5 left over. Took out the 5 and the 12, had 31 left over. So everything should be exactly backwards. but we end up with very different processing. In a small example, we can see them all, but remember, this is gonna be big examples. Another thing we do is try to find a big data set so that we can see our charts on like the task manager actually move. See those plots from the RAM access, so something with some public government data that's gonna have 300 million data points about all the Americans. So that we can actually see our RAM, the meter of the RAM get bigger, and then how it empties out with these structures versus our other ones. But basically, two structures sort of the reverse of each other. And then I had a short example in mind for a customized version of this. Shouldn't take us more than 10 minutes here. There's just a couple lines because you see there's not really much to a stack or a queue. But again, just like we saw with lists, the reason we would look at it is to do some custom stuff. I'll save this now so I don't forget to do it later. I'll do a stack, but like we just saw with that comparison, the difference between the two would just be sort of a reverse order if we're doing the whole thing every time. So say we had some employee data that we want to go track. It's actually that file we did the other day, right? We use when we were looking at the issue with error handling, we went ahead and created this little text file here. I had just a few names and what looks like pay rates in it. So we're going to pretend that's our database. And for a company that's a good sized company that would need custom software, that'd probably be 40,000 names or rates of pay, not just 4, but the same pattern would just repeat over and over and over again. And so this one will fit in our class example. So we have this big database full of employees and rates of pay. So actually what we saw the other day would be a good start to that. We could read that in. Where was that example? I think it was this one. Open that one. Oh yeah, this will work. So kind of a critical thing. That point we looked at the other day, we're going to try to open the database and grab our data, but if something happens, we'll recreate the database. And hopefully y'all can see that it wouldn't take much to make that dynamic. Like whatever our functionality is to add new employees to that database could just go over to this file and parse through this file and add it into the text here as well. It's just a text file. We can change our code dynamically. And every time we add something to the database, automatically add it here in that section of code we hope will never ever run. But if it does, it fixes the problem of the missing database. What we looked at the other day. But once we have our data, we're going to do something with it. So I'm going to create a class. I'll call it crew, to kind of show it's an extension of the thing the other day. I give it the same name. An employee object often makes a good example, something easy to visualize, but employees don't come in singular format. Employees come as a team or a crew, or usually more than one. So we can set this up to sort of work as a stack. I'll do like a payroll thing. So we have that bigger object, it's a list. that we worked last time, but maybe we can do we'll set up a payroll processing as a stack. So we have our database, and we saw it's a nice safe way to keep our database, because if it gets lost, the software will automatically recreate it. And well, last week's homework that everybody did amazing jobs on, by the way. Great job, y'all, on that. Everybody that's here this evening added some functionality to that last week's homework. That all of it looked really good too, which is really nice to see, because it's like, yeah, y'all, it could have been a really easy assignment, and y'all all looked at it and was like, okay, I need to do more than this, to the point you want to add stuff to it. So I was really glad to see that. But this Python script is just a text file. We could add stuff here with no problem when our software does other stuff, but y'all know how to do that. So again, just like our list, I'll set up an empty thing to serve as our stack. Folks, is an empty stack, empty list at this point, but we'll use it as a stack. So then we need a couple methods. I'll say push folks. Define full payroll file. Anything else on there? No, this should be good. We have those lists and stuff. I'm just gonna do it right this way. So to push these on there, we'll kind of run through our entire list. Oh, we don't need this part. All of this stuff. Oh, cut. And instead of just printing it out, we'll add it to our list. And it's a stack, so we want to put it in at the beginning, so we can pop it off easily. So insert that at index 0. I need to split it, don't I? Name is only half of it. So imp 0, 0. I want both of them. There we go. Sorry, I started to confuse myself. I started thinking about wanted to do two things, but I'll just do it that way. I'll let y'all look at that for a second. So we're going to read the next line, which has name and pay rate, split it at the comma, and then put those in there. We don't need index 0. That was just the name part. So then each item on our stack is a two-dimensional list, or yeah, and a list with 2 elements building up our stack. And we saw that that line was just for the error handling. So kind of like we saw the other day, the only difference is we're actually doing something useful with this instead of just printing things out. Which is L at this point. So we'll read all that in that data, split it into commas so that each thing in our, each item in our stack is I'll put N and R. N and R. So then we have a stack of list with 2 elements each, the name and the rate of pay. Then for popping things, to say if the length of that. So I did want to change this up a little bit. So I've got folks is equal to 0. So instead of putting in that peak in the size, I'll just put that right in the pop method. When we get to the end of the list, there's just nothing else to pop off there. Don't need to worry about anything. My plan is to run it in the console. We'll let it run, get all our data, and then we'll get a bunch of input prompts show up in the console asking us to, or giving us this information. Yeah. Return. That's all for now. Otherwise, we want to pop stuff off the stack. So like our current thing is self dot underscore folks. The very first one in there. And that's going to have 2 elements, the name and the list. So we'll need to split it up. But then just like we saw before, we want to take that out of our list. Remove current. So those are the things we saw before, and then we just print out a string. So like hours is float. I'm thinking about that backwards. Input. Please enter plus current 0 is the name plus apostrophe S hours worked. Why didn't that do that? There we go. And then there's some casting needs done here. That needs to be a string. Which I switched back to this instead of the print F. I can't remember if I said it here or not. But in the SDEV 120 class, I started to do the print F line and confused some people new to programming very, very quickly. You all know about the better formatting, so I'm just going to do this one so I don't accidentally do that and confuse people just getting started into programming again. Because it's much more confusing to them because you all know multiple ways to format, to concatenate together strings. So I can show you all the way I need to do it in the other class, and then not accidentally slip up and do a complicated thing or a messy looking thing on people that's like the second or third day they've never seen any Python code. Oh, then that needs to be a float. Same thing on this next one. So we're going to get some input, say, oh, actually, no, I already have it. Current 0 is not 0, 1 is the rate of pay times hours, but that's a floating point number. And oh, then I'll return it. I'll return it the other way. Current 0, which is name, made $ gross is a period. Okay, so I think that it got all the points there. So you'll notice that in the pop method, I went ahead and included the peak and length or peak and size there, just in that if structure. So if there's nothing left, then return that. So that's like the peek ahead to see that there's nothing there, because this is a very focused purpose thing. But it loads our data from storage, the place where data should be kept, brings that in, quickly asks for the one number that's not going to be in long-term storage, or how many hours were worked, and then spits the result back out. And it's a stack, so it doesn't keep it in memory any longer than it needs to be there. I'm going to add 2 lines here. Yeah, they're already there. I have a return statement, so actually it would cause problems. I was going to add these 2 lines. Delete current, and then garbage collection dot collect. So delete marks it, says we never need this again. And then garbage collection, if that's the very next line. The very next line in our script, but I've made a comment at least twice this semester now about with modern computing, we have to be careful sometimes, because the next line in our script does not necessarily mean the next line through the CPU. I mentioned earlier about all of the different software running concurrently, which you all are well aware of. There's lots and lots of things happening at the same time. So the next line in our script, we don't have a guarantee that the next line in our script is the very next line that's going to run. So we do have to be careful about things sometimes. Most notably, closing files can be a big issue, but here, the very next line, so we mark something and say, we're never going to need this again, and garbage collection deletes it immediately. So the things we have in storage where it's the proper place to keep data around, probably is a JSON file, because we talk about looking at a whole bunch of different versions, but in our world, we use JSON and Python because they're easy to work with. Everybody does that. It's just in the classroom, we have to see a bunch of them. So over in that JSON file, we grab our stuff, bring it in, work with it, and then immediately delete it from RAM because it's over in storage. We don't need to keep it in RAM, wasting space when other stuff. Our Zoom call could do that. Dozens of pieces of software on our computer could be checking for updates with those few bits of RAM that we're wasting on data that we've already processed. Or in really big sets. I'm seeing if on Thursday, if I can try to find a version, a bunch of good government data that would have, like all of America's population in it, so that we at least have a couple examples of 300 million data points to look at in our class examples. Okay, so ran that. So we need a version of this. I'll call it team. Is going to be crew. So we have one of those. Team.push folks. So it's in the up in the variable explorer. We have our file path to where the database is. And we have our objects. So we can call this push folks method, which I did in Pascal case. Doesn't show us any other things, no error message. So at this point, we should have a bunch of data there to work with. So if we call the other one team.payroll pop, nope, that's not how I spell it. Pop. Okay, so enter Becky's hours worked, and Becky worked 38 hours. We get her pay. Call payroll pop again. You work 23 hours. Get his rate of pay. Call that again. 44 hours. Get his rate of pay. Call that again. 21 hours. Maybe she took half the week off. Call that again. Oh, and that's all. So that's the big one right there. That's what all that stuff was leading up to. Does that seem different than the way you would have handled multiple inputs in the past? In the console? And obviously we can take that right over to a graphical user interface with no trouble. But we just set everything up. And then it was just a matter of calling that same method. At this point, we have a stack of the data we need. So everything's stacked up. And then we just pop the stuff off the stack one at a time to work back to it. So customizing stacks is why we look at them, but usually classrooms, we want to talk about the vocabulary and stuff, so we just see the generic examples. But hopefully this gives you a better idea of what to do with those generic examples. Right? Our exception handling doesn't print out a message that says couldn't find the file, which is essentially the default thing anyway. If the file's gone, our file handler actually fixes it, right? We saw that the other day. If somebody new at work and accidentally deletes the database, we still have it. Team is a crew object. Team dot push folks onto our stack. Then we can do team dot payroll pop. Enter the numbers 32, 39, 41, 28. Oh, whoops. I should be pushing up. So the next thing would be 39. Push up. Give me that. Then 41. Then call that last method again. Enter 28. Call that last method again, and we get a message that we're done. So even though the database was deleted, the software corrected itself and then very efficiently moved things through our database in order to keep track of them. I guess I could try this. I was going to try putting a breakpoint in there and just step through with the debugger so we can see some other stuff in the over in the variable window. We all know how to do that. And at least two of the people on the screen, the names I see right now, are using VS Code. So you have some other debugging tools you could use if you want to walk through that and kind of see that. But hopefully that last example there makes sense as to the usefulness of it. We customize our classes. We just build the stuff up that way. But that was, I guess that brings us to a good stopping point. A queue would do exactly the same thing. We can do a queue the same way, just start and just, it goes in the other order. The first thing we put in there is the first thing that gets processed. But RAM is empty when we're done. We don't keep it around. Hopefully that makes sense and you can see the usefulness of it. Does anybody have any questions about that? Okay, and we got through stacks and queues. So there's some other data structures. We definitely don't have time to talk about all of them. Anybody going on for a 4-year degree in software engineering or compute is probably an elective in computer science, depending on the school. Might be required in computer science, definitely required in 4-year computer or software development or software engineering. And at the very least, an elective is an entire semester on data structures. And usually it's a high level class, so the professor goes in there and kind of talks like an auctioneer. Talking as fast as they can for the entire semester, and it still can barely cover every data structure that's in it. There's a lot of. So we got a little bit of time. We got some more to look at. Look at some trees, some basic trees to start with. A few more. We'll continue from here on Thursday. I had to think about what day it was. Unless anybody had any questions for this evening, that should be it. Okay, I assume the silence means no questions. So y'all have a great evening. I hope you see the usefulness of that generic thing we were studying with that final example there. And I'll see y'all on Thursday.